Hi everybody, welcome back for AP Chemistry. This is Tyler Chase and you're here for Senior Takeover Day. Today we're going to talk about electrolytic cells, and so get ready for the ride. You ready for this? Here we go. Batteries are simply self-contained electrochemical power sources that have one or more galvanic cells. Normally, we have to use small voltages in electrochemical cells. So what we do is we put more than one cell all in a row. So if we are only getting like 0.2 volts, then we would want to add up to 1.5 volts. So we'd have to have a bunch of those all strung together, right? It's called a series circuit. So we add the potential, we add all of the voltages together. So the voltages are additive when the batteries are connected due to a continuation of the flow of the electrons. We can simply take the potential of one electrochemical cell and add it to the next electrochemical cell in our series. A fuel cell is different from a battery. You see, a battery has all of the energy already packed inside it in the chemical bonds. But a fuel cell has to have fuel added to it to convert that chemical energy into electrical energy. In other words, it's not self-contained. It produces current, though, uses combustion or electron excitation to produce the chemical energy. Holy smokes. Now let's look at corrosion. Corrosion is a spontaneous redox reaction in which a metal is attacked by some substance in the environment and converted to an unwanted compound. So this is just going to happen. That's like when oxygen reacts with iron, it's just going to turn to rust. But there are ways that we can prevent this. If we had something that oxygen would rather bond with, then we would call that a sacrificial anode. Some metal that's more active can be used to prevent the corrosion of the metal that we want to preserve. So imagine if we had like a pipe laying in the ground. We don't want that pipe to corrode. That would be a really good place to put a sacrificial anode, because we want to protect it and preserve it. We don't want to have to replace it, but underground there's a lot of moisture and stuff, right? So we've got to protect it, and it's usually magnesium that's used for that one. Now in electrolysis, this is where we would use electricity to cause some non-spontaneous reaction to occur by driving the reaction in the opposite direction. This is the whole idea of having a rechargeable battery. The spontaneous direction is to use up the energy, but we want to recharge the battery, to put more energy in. So what do? You plug it in, you add more electrons to it, and you force it to go backwards. So in an electrolytic cell that's used for electrolysis, you won't have a positive cell potential, you have a negative cell potential. And we connect the cathode and the anode backwards, right? Instead of connecting the cathode to the positive, we connect it to the negative. So the cathode is still going to get reduced. We just have to put it on the side of the reaction that's going to actually be doing the reducing. In a voltaic cell, the cell potential is positive. And I can't spell. Voltaic. You know what I mean. All right, so let's compare the two. The galvanic cell has the cathode on the left, and the cathode is on the right and the anode is on the left. Notice how iron is losing electrons to the copper. So the thing that is reduced is our cathode. Copper is our cathode. We still add the cell potential in the same way. So I've taken the cathode minus the anode. So we get 0.78 volts. For a non-spontaneous reaction, though, we're making the electrons go the opposite direction. So what we see is that the cell potential has a negative sign now. These calculations, though, with electrolysis are pretty easy. The electrolytic cell, basically, in your calculations, you're going to need to know a few terms, and then you're going to find them really easy. First of all, an ampere in physics is the units that are used to measure current, the flow of electrons in coulombs per second, where coulomb refers to the charge and seconds refers to the time. So it's charge over time. How many electrons are passing a certain point at any given time. So it's measuring the rate of electron flow. Faraday's constant is then what we use to go from coulombs to moles. And so this is really handy. It gives us another way to get to moles, and that's what we're always after in chemistry class, right? How do we get to moles? When in doubt, go to moles. And so if we can get to moles, we can go anywhere. Here's an example. It asks us to calculate the amount of time required to produce 1,000 grams of magnesium metal by electrolysis of molten magnesium chloride using a current of 50 amps. So this is something we might do in a factory, in a steel factory, where we melt down some ore of magnesium so that we can get the magnesium out of it. So we start with magnesium chloride and we turn it into magnesium and chlorine. And chlorine is a Brinkelhoff guy, right? But let's think about charge and how charge works. Magnesium was a 2+ here. The magnesium metal turns into a 0 charge, and then chlorine's just a spectator, so we'll leave that guy out. So, of course, to get rid of a 2+ charge, we've had to add 2 electrons. So let's start with 1,000 grams of magnesium metal, because I see right away how we can turn that into moles, right? Grams to moles we can do. So 1 mole of magnesium has a mass of 24.3 grams. And then in our next step, we have to remember how many moles of electrons it took. So for every mole of magnesium, I needed to have 2 moles of electrons. Now let's go to coulombs. Use Faraday's constant. For 1 mole of electrons, I need 96,485 coulombs. Finally, we can go to time now using amperes. Remember, 1 amp is the same as 1 coulomb, as 1 coulomb per second. So we take 50 coulombs on the bottom to cancel coulombs, and 1 second on the top. We're going to end up with units of time. The trouble is, I got a lot of seconds here. 158,823 seconds. Wow. Let's divide that number by 60 so that we can get a more manageable unit of time. So how about minutes? Let's see how many minutes. 2,647 minutes. We don't usually keep time that way. Divide by 60 again. Do we get something we can use? How about 44 hours? Still not good enough. 24 hours in a day, right? And so how about 1.83 days? If this is really your magnesium factory where you are making magnesium and all you make in 1.3 days is 1,000 grams, we're not going to make a very big profit. I think we should turn up the electricity. Let's look at another example then. Okay, so our solution is electrolyzed using a current of 7.60 amps. What is the mass of chromium plated out after 2 days? So remember, let's write our equation to show how many electrons move, and we want to get to mass this time. Last time we were going to time, so let's start with time. We always use amps as a conversion factor, never a starting place, only a conversion factor. So 2 days, we better change that to seconds so that we can use amps. 1 day is 24 hours, And 1 hour has, oh, why am I trying to decide? Let's see. 1 hour is 3,600 seconds. All right. Now I can use amps for a conversion factor. That's 7.60 coulombs per second. And I need seconds on the bottom to cancel. 7.60 coulombs on top. And now it's time for Faraday's constant. We got to change coulombs to moles now, right? That's what we're always after. How do we get to moles so that we can solve our problem? So 96,485 coulombs per mole of electrons. And I said I was going to write the reaction, but I didn't. Chromium 3 plus turns into solid chromium when we add 3 electrons to it. Here's the part where we needed that. If 1 mole of electrons makes 96,485 coulombs, then I need to account for 3 moles of electrons being there. And now we can go to mass. No, we can't. We're going to moles of chromium. Oh yeah, we can go to mass now. 52 grams of chromium for every mole of chromium. And so we do the top times the top and the bottom times the bottom. And I ended up with 235.9 grams of chromium, and so in 3 sig figs only, that would be 236 grams. So that's how we work with electrolytic cells. Those are pretty commonly used in a follow-up question for free response, like part D or E or F. But they'll be pretty easy. It's just a big long T table. So why would we use electrolysis? We do this to put some thin coating on an existing metal to help protect it. So we take the metal that we want to protect and coat it with a thin coating of some other metal. So we attach the metal to the cathode and put it in a solution of other ions like it. So if you want to plate out copper, you would put a copper metal in copper ions that are in solution. Hey, no more AP Chemistry notes. This is it. Good luck on your exam, guys. Thanks for a great year.